Hello, this is Jack Jackson. In this video we're going to start a series of videos talking about integration and anti-differentiation. So one of the main focuses of these videos is to reverse the shortcut rules we developed for finding derivatives to be able to compute antiderivatives of a given function, and we will use these antiderivatives to find exact values for definite integrals, making use of the fundamental theorem of calculus. And in these videos we will cover all the basic integration techniques, including all basic functions, substitution, integration by parts as well. More advanced techniques are usually covered in a Calculus 2 class, and I may add a video about that at some point in the future. In the previous set of notes we've seen that a definite integral is defined as a limit of right Riemann sums as the number of rectangles approaches infinity. So the definition we were using in those videos is this. For a definite integral, we let delta x be b minus a over n, so that delta x is the width of each rectangle, so that we divide the interval a to b into equal intervals of equal width. Then x sub k is a plus k times delta x, so that x sub k is the x value at the right end of the kth rectangle. Then when we do f of x sub k, that becomes the height of the rectangle, or assigned height technically, and then we multiply by the width delta x, so that product there becomes the area of the rectangle, or at least a signed area of the rectangle. Then we sum those up and we have what's called a right Riemann sum. We take the limit of that as n goes to infinity and we have a definite integral. Notice the notation here. The delta x becomes the dx over here. The f of x sub k, we drop the sub k and just make it f of x. The summation here, this s becomes a long skinny s, the integral sign over here. The limit's already taken, so the n's out of the picture, but it's all based on the a and the b here to begin with. So that's the definition, somewhat simplified definition maybe that we were using in the last set of videos. But we should keep in mind that this is the actual definition of the definite integral. Anything that we do to find a definite integral that's not going by the definition is actually a shortcut in some ways. But in practice, one never evaluates a definite integral directly by the definition. Instead, what we do is we use the fundamental theorem of calculus and antiderivatives to compute exact values of definite integrals when we desire to have an exact value. And we will investigate and practice these techniques much more in this set of notes, in this set of videos. However, also realize that if the only thing desired is a decimal approximation of the definite integral, as is often the case in most application problems, then a numerical integration approximation technique, such as the version of Simpson's rule that's built into your calculator, is sufficient and often easier to use. Furthermore, as we have seen, some functions do not have antiderivatives built up out of elementary functions. So this method of using the fundamental theorem to find the exact value of the definite integral is impossible in those cases. So in those cases, a numerical approximation technique is the only option available. So in conclusion, we use the fundamental theorem of calculus to evaluate a definite integral when we want an exact value and we can find an antiderivative of the integrand. On the other hand, if we only need a decimal approximation of the definite integral, or we cannot find an antiderivative of the integrand, then we apply a calculator approximation technique. So let's review the fundamental theorem. The fundamental theorem of calculus says, let f of t be a function that is continuous on a closed interval from a to x, then the derivative of the integral of a to x of f of t dt is f of x. So if you integrate first into a derivative, you're back where you started, basically. And part 2 is the reverse of that. If we take a function f and take its derivative and then integrate it from a to x, we're back at f of x, well, sort of. We're back at f of x minus the constant f of a. The last part here can be written equivalently this way. If f is any antiderivative of a continuous function g, okay, that means g is the derivative of f prime equals g, and f is an antiderivative of g. Then if we integrate g from a to b with respect to x, then what we get is the total change in the antiderivative f. We get f evaluated at b minus f evaluated at a. This last part here is going to give us a way to find exact values for definite integrals. Okay, so according to the theorem, the only thing we have to do to evaluate a definite integral is get our hands on some antiderivative of the integrand function, and then just simply evaluate it at both the upper and lower limits of the integral and subtract. Well, evaluating a function and subtracting are typically pretty easy things to do, or at least very straightforward. So the real task then just becomes finding this antiderivative function. So the process of taking a function and finding its antiderivative is exactly the inverse process of taking a function and finding its derivative. This process is probably more properly called antidifferentiation. However, because of its close relationship to definite integrals, this process is also known as integration. So, before we continue on, we need to remember that two functions have the same derivative if and only if they are vertical shifts of each other. In other words, they differ by a constant. If you think about it, they've got the same, for a particular x value, if the derivative is the same, they have the same slope there, they have the same tangent line, and if you zoom in close, they both look like the same, not the same tangent line, but parallel tangent lines. Okay? If this happens at every point on there, basically means they have the same shape. So they have to be just vertical shifts of each other. So while the process of taking a function and finding the one and only derivative of that function is itself a function, the process is a function, that process is not a one-to-one function. So the inverse relation of taking a function and finding its antiderivatives, plural, is not a function. It produces an entire family of antiderivatives for each function, all differing by a constant. So we borrow from the notation for definite integrals, and we say the family of antiderivatives of a function f, also known as an indefinite integral, is given by this following notation. We use an integral sign of f of x dx. Well, what's different in that and the definite integral? It's missing the limits. So when it's missing the limits, it's really an antiderivative or a family of antiderivatives that we're computing here. So we have a couple of things here that we have in general. So what do we mean? If we take this family of antiderivatives, any one of them, and we take the derivative, we're back at the original function f. That's what that antiderivative thing means. So that means if we take a derivative of g and then take an antiderivative, we're back at g, well, or some shift of g. So notice that the antiderivative or indefinite integral notation gives an entire family of derivatives. We always are going to have this plus c there. So let's look at a very simple example. The family of antiderivatives of x dx, or the indefinite integral of x dx, the family of antiderivatives of x, is 1/2 x squared plus c. Well, how do I know this? Well, I know this because if I take the derivative of the answer, 1/2 x squared plus c, then I am right back to where I started at x. See, check it out. The derivative of 1/2 x squared plus c, well, first of all, the derivative of c is 0. That always happens. And then you take the derivative of this, we use the sum rule to break it into two parts, then the constant multiple rule and the power rule. So we get 2 times 1/2 is 1, power goes down to 1, derivative of c is 0, and so we just get x. And of course that's a pretty easy derivative to find, and we know that that is an antiderivative. So the family of antiderivatives will always have that plus c in the answer. So anytime you're doing an antiderivative or indefinite integral, we always have that plus c where c is some arbitrary constant. Now, what if we want a specific antiderivative? Well, to do that, we don't know what the c is. So to find that c, we need something else, some other piece of information that we would call an additional condition. We need a value of x and So an f of x, let's say f of x is this antiderivative that we're looking for. If you give me a value for x and f of x, and x and y, in other words, on the antiderivative, you can use that to solve for c. Now, we can use this example that we just did in the fundamental theorem of calculus to evaluate the definite integral. So the definite integral from 1 to 4 of x dx, the fundamental theorem says get our hands on an antiderivative. Well, all of them look like 1/2 x squared plus c, and we evaluate from 1 to 4. This first line right here, this part on the right side, is just a shorthand notation for what you see on the next line, which is take this function, plug in 4, minus, plug in 1 here. So evaluate it at the top number and the bottom number separately and subtract. So here we distribute the minus, and notice that the c's cancel out. That always happens. 4 squared is 16 divided by times 1/2 is 16 halves, and this is 1/2 times 1 is 1, and the minus here makes it minus 1/2. The minus times the c is minus c, the c's cancel. 16 halves minus 1/2 is 15 halves, or 7.5. And this is an exact value for this definite integral. Now notice that the c always cancels out. So what that tells us is we can use whatever value of c we want, whatever's most convenient. And most of the time the one that's most convenient is to just let c be 0. Once we get our hands on any antiderivative, don't worry about the plus c in this process. It would have been exactly the same thing if we'd never written the c there. But don't forget the plus c if you're back up here finding the family of antiderivatives. But we can ignore the c in this computation here for a definite integral. So the key to finding definite integrals is in finding antiderivatives. So to find antiderivatives, we need to reverse the derivative shortcut rules. Note that every derivative rule results in a corresponding antiderivative rule. And below, we're going to look at the basic derivative rules and the corresponding antiderivative rules that result from them. So we'll look at that in our next video and then put it to work in the video after that.